Hello everyone, I am Dr. Ranganath Haridas, working as Assistant Professor in SVERI's College of Engineering, Pandharpur. Today we are discussing one of the topic related to physics. Its name is atoms, molecules and nuclei. So let us check these points one by one, the basic terms, its equations, and then we check some MCQs with its solutions. Let us start with the list of points whatever we are discussing. So Rutherford's alpha scattering experiment we have to check, then distance of closest approach, that is nuclear size, impact parameter, then what is the composition of nucleus, atomic number, atomic mass number and atomic mass unit, radius of the nucleus and nuclear density, mass energy relation and mass defect. Next is binding energy and binding energy per nucleon, binding energy curve, then nuclear forces, radioactivity, then Rutherford and Soddy's laws of radioactive decay, radioactive disintegration constant, and what is meant by half-life period, units of radioactivity, then nuclear fission and nuclear fusion, and last but not the least, that is what is meant by de Broglie wavelength and Davison-Germer experiment. So let us start discussing these points one by one. Rutherford's alpha scattering experiment gives us idea about the scattering of these particles. So if we check the figure, lead box is there and we are using bismuth or radon alpha beam. We are bombarding on thin gold foil. ZNS screen is there on which we are recording things. So if we check the gold atom at micro level, if we discuss, so this figure gives us the idea that how these alpha beams gets scattered. They go back from the center of the gold atom and how they get scattered. If we check the graph, which is scattering angle theta versus number of alpha particles scattered, that is n, so we can get the idea as the angle increases, so exponential decay is there and we are getting number of alpha particles which are scattered at lowest angle as we are getting, and as angle increases we can get the structure of graph like this. So let us move to the next one. So alpha particle is a nucleus of helium atom carrying a charge of +2e and mass equal to 4 times that of hydrogen atom. It travels with a speed nearly 10 raised to 4 meter per second and is highly penetrating. So if we compare Rutherford experiment and Geiger and Marson experiment, so what we are getting, source of alpha particles in case of Rutherford experiment is radon. In case of next experiment, that is Geiger experiment, it is bismuth. Speed of alpha particle is 10 raised to 4 meter per second. Here in this case 1.6 into 10 raised to 7 meter per second. Thickness of gold foil we are using for Rutherford experiment is 10 raised to -6 meter. For Geiger experiment it is 2.1 into 10 raised to -7 meter. आपण काय डिस्कस करतोय तर रुदरफोर्ड अल्फा स्कॅटरिंग एक्सपेरिमेंट, ज्यामध्ये आपण जो अल्फा पार्टिकल सोर्स आहे लीड बॉक्स मधून आपण तो यूज करतोय. अल्फा पार्टिकल्स जनरेट होत आहेत आणि त्याला आपण एक्सपोज करतोय, बंबार्ड करतोय थिन गोल्ड फॉइलवर. ZNS स्क्रीन आहे ज्याच्यावर आपण तो पॅटर्न रेकॉर्ड करतोय. जर अल्फा पार्टिकल्सचं स्ट्रक्चर जर बघितलं, जसं आपण त्याला एक्सपोज किंवा बंबार्ड करतोय गोल्ड ॲटमवर, तर आपल्याला दिसते की अल्फा पार्टिकल्स जे आहेत तर ते स्कॅटर होत आहेत वेगवेगळ्या पोझिशनला. ग्राफ स्कॅटरिंग अँगल वर्सेस नंबर ऑफ पार्टिकल्स इंडिकेट करतोय. आपल्याला इथं ग्राफवरून लक्षात येते की जसं जसं अँगल चेंज होईल स्कॅटरिंग अँगल, त्यानुसार नंबर ऑफ अल्फा पार्टिकल्स कसे स्कॅटर होत आहेत. दोन एक्सपेरिमेंट जर आपण कंपेअर केले, रुदरफोर्ड आणि गॅगर, तर त्यामध्ये अल्फा पार्टिकलचे सोर्स आपण वेगवेगळे यूज केले. त्याचा स्पीड आणि थिकनेस गोल्ड फॉइलचा जो आहे तर तो आपण वेगळा वापरलेला आहे. So what are the observation and conclusion? Most of the alpha particles passed straight through the gold foil. What is the conclusion? It indicates that most of space in an atom is empty. Next observation, some of the alpha particles were scattered by only small angles of the order of a few degrees. What is the conclusion? Alpha particles, being positively charged and heavy compared to electron, could only be deflected by heavy and positive region in an atom. It indicates that the positive charges and the most of the mass of the atom are concentrated at the center called the nucleus. Next, a few alpha particles, 1 in 9,000, were deflected through large angles even greater than 90 degree. Some of them even retraced their path, that is angle of deflection was 180 degree. What is the conclusion? Alpha particles which travel towards the nucleus directly get retarded due to Coulomb's force of repulsion and ultimately comes to rest and then fly off in the opposite direction. So in the first observation, most of the alpha particles are passing in straight line through the gold foil. So it means that in an atom there is a much space which is available so that alpha particles are passing in straight line. Then some of the alpha particles were scattered by only small angles of the order of a few degrees, and few alpha particles were deflected through large angles, that is alpha particles which travel towards the nucleus directly get retarded due to Coulomb's force of repulsion and ultimately comes to rest and then fly off in the opposite direction, which is shown in our figure of first slide. They move to the opposite direction, that is fly off in the opposite direction. The next distance of closest approach, that is nuclear size. So when the distance between alpha particle and the nucleus is equal to the distance of the closest approach, the alpha particle comes to rest. At this point or distance, the kinetic energy of alpha particle is completely converted into electric potential energy of the system, which is given by the equation below. So what happens when the distance between alpha particle and the nucleus is equal to the distance of the closest approach? The alpha particle comes to rest. So here what is happening, that alpha particle is coming to rest according to the distance of closest approach. Then we will check the composition of nucleus. So first we have discussed these terms, that is Rutherford's alpha scattering experiment compared to other experiment, then the observation and conclusions, and the distance of closest approach. Now let us discuss some basic terms, that is composition of nucleus, atomic number, atomic mass number, and what is meant by atomic mass unit. Every atomic nucleus except that of hydrogen has two types of particles, that is protons and neutrons. Nucleus of hydrogen contains only one proton. Proton is a fundamental particle with positive charge 1.6 into 10 raised to minus 19 coulomb and mass 1.67 into 10 raised to minus 27 kilogram. That is 1836 times heavier than an electron. In case of neutron, neutron is also a fundamental particle with no charge and its mass is 1.675 into 10 raised to minus 27 kilogram, which is 1840 times heavier than an electron. So if we check the proton and neutron, which are the basic blocks of nucleus, so these particles which are having positive charge, that is proton with its mass, and for neutron it has no charge, its mass is also given. Then let us check what is meant by atomic number. The number of protons in a nucleus of an atom is called atomic number. The atomic mass number is nothing but the sum of number of protons and number of neutrons in a nucleus of an atom. It is called the atomic mass number. So if you consider atomic number as it said, that is number of protons, and atomic mass number as capital A. So its sum means capital A is nothing but Z plus N, where the sum of number of protons, that is Z, and number of neutrons, that is capital N, gives us atomic mass number. Next, atomic mass unit. So how we can determine this? So atomic mass unit is nothing but 1/12 mass of an atom of carbon, where we are writing this as one atomic mass unit is equal to 1 divided by 12 into 12 divided by 6.023 into 10 raised to 23. So after calculation we are getting it as 1.66 into 10 raised to minus 27 kilogram. So we have discussed the composition of nucleus, where this nucleus contains protons and neutrons with its charge value and its mass value. Then we have discussed atomic number and atomic mass number, where number of protons in nucleus of an atom is nothing but atomic number, and the sum of number of protons and number of neutrons is nothing but atomic mass number. Atomic mass unit is nothing but 1/12 mass of a one carbon atom, which we have calculated. So next is size of nucleus. So nucleus does not have a sharp or well defined boundary. However, the radius of nucleus can be given as r is equal to r0 a raised to 1 by 3, where r0 is nothing but 1.2 into 10 raised to minus 5 meter, which is a constant which is the same for all nuclei, and a is the mass number of the nucleus. So if we consider radius of nucleus, it ranges from 1 mm to 10 mm. Nuclear volume, if we check, so we can get this value, that is V is equal to 4 by 3 pi r cube. So 4 by 3 pi r0 cube into capital A, where V is proportional to capital A. So that is size of nucleus. Then in case of density, if we discuss, so the density of nucleus is mass of nucleus, that is M is equal to A atomic mass unit, so A into 1.66 into 10 raised to minus 27 kilogram. So nuclear volume, if we calculate, so it is V is equal to 4 by 3 pi r cube, that is 4 by 3 pi r0 cube into A. So if we put the values, we can get the answer. And if we determine the nucleus density, that's rho is equal to mass upon volume, so we can get the value as 2.29 into 10 raised to 17 kilogram per meter cube. So in this slide we have discussed the size of nucleus and nucleus density. So size of nucleus we have discussed as r is equal to r0 into a raised to 1 by 3, where we are discussing about the nuclear volume first, and mass upon volume we can determine the nucleus density. So let us discuss these points. The nuclear density does not depend upon mass number. So all the nuclei possess nearly the same density. The nuclear density has extremely large value. Such high densities are found in white dwarf stars, which contain mainly nuclear matter. The nuclear density is not uniform throughout the nucleus. It has maximum value at the center and decreases gradually as we move away from the center of the nucleus. The nuclear radius is the distance from the center of the nucleus at which the density of nuclear matter decreases to one half of its maximum value at center. So in this discussion, we are discussing these 4 points. First is nuclear density does not depend upon atomic mass number. So all nuclei possesses same density, nearly the same density. The nuclear density has extremely large value. Such high densities are found in the white dwarf stars, which contains mainly nuclear matter. Next is the nuclear density is not uniform throughout the nucleus. It has maximum value at the center and it decreases gradually as we move away from the center of the nucleus. And the fourth one is the nuclear radius. So it is a distance from the center of the nucleus at which the density of nuclear matter decreases to one half of its maximum value at the center. So let us move to the next point. It is mass energy relation. So when we are considering the equation E is equal to mc square, which is energy mass equivalence. So before considering that equation directly, first we have to discuss what is meant by the relativity of mass, because relativity of mass gives us the idea about the variation of mass with the variation of velocity, and by using this equation only we are moving further to prove the energy mass equivalence, that is E is equal to mc square. So this relativistic mass equation is m is equal to m0 divided by under root 1 minus v square by c square. So how we can get this? So according to Newton's second law of motion, force acting on a body is defined as the rate of change of momentum. So in case of classical mechanics, if we check, that is F is equal to d by dt of mv. But here with v, m is also variable for the special theory of relativity, that is Einstein's theory of relativity. So if we consider the equation, that is rate of change of momentum, as F is equal to d by dt of mv. So here m into dv by dt plus v into dm by dt. If this force capital F displaces the body by a distance dx, its energy increases by, so the change in kinetic energy if we are discussing. So if this force F displaces the body by a small distance, that is dx, so we can get the equation as dk is equal to capital F into dx. But just we have defined what is meant by F, which is nothing but m into dv by dt plus v into dm by dt. So put value of F in this next equation, what we are getting? So m into dv by dt into dx plus v into dm by dt into dx. So we are adjusting the terms. We are writing this dk as m into dx by dt into dv here plus v into dx by dt into dm here. So as we know that dx by dt is nothing but v. So we are writing this equation further as dk is equal to mv dv plus v into once again v, that is v square dm. So this we are writing the change in kinetic energy, that is mv dv plus v square dm. Next, according to Einstein's relation of relativistic mass, so according to Einstein's relation of relativity, its equation, that is relativistic mass equation, is m is equal to m0 divided by under root 1 minus v square by c square. So let us move to next slide, that is squaring and adjusting the term of this equation, last equation of this slide. that is m is equal to m0 divided by 1 minus under root 1 minus v square by c square. So if we square this, it becomes m square which is equal to m0 square divided by 1 minus v square by c square. So after adjusting this term, we can get this equation as m square c square minus m square v square, which is equal to m0 square c square. So differentiating this equation by considering as m0 and c is constant, so it becomes c square twice m dm minus m square twice v dv minus v square twice m dm, which is equal to 0 as m0 and c both are constants. So by further adjusting, that is removing twice m from each and every term, we are getting c square dm minus mv dv minus v square dm, which is equal to 0. So we are adjusting this equation as c square dm, which is equal to mv dv plus v square dm. So if we compare equation 1 and 2, so first equation is here, that is dk is equal to mv dv plus v square dm, and second equation is c square dm, which is equal to mv dv plus v square dm. So RHS is same, so if we compare this, we can get LHS as dk is equal to c square dm. So that equation we are getting, which is nothing but change in kinetic energy. So if particle is accelerated from rest to a velocity v, let its mass m0 increases to m. So integrating so that we can get total kinetic energy. So total increase in kinetic energy is nothing but integration of dk, which is equal to c square into integration of dm from m0 to m. So it simply becomes k, and by solving this, we are getting m minus m0 into c square, or simply k plus m0 c square is equal to mc square. Here m0 c square is the energy associated with the rest mass of the body, and k is the kinetic energy. Thus the total energy of the body is nothing but simply E is equal to mc square. So this is called as Einstein's mass energy equivalence equation or relation. So how we can get that? First, we have considered the rate of change of momentum by considering mass is also in variation with the motion of that particle or an object. Then we have used the value of force in change in kinetic energy equation, that is dk is equal to f into dx. After putting this, adjusting the term dx by dt as v, we got equation number 1. Then we have considered the relativistic mass equation, m is equal to m0 divided by under root 1 minus v square by c square. Squaring and adjusting this term, then differentiating, we get this equation. Taking twice m common, we get further one, and adjusting it, we get equation number 2. So if we compare equation 1, that is dk is equal to mv dv plus v square dm, and equation 2, that is c square dm, which is equal to mv dv plus v square dm, RHS is same, so we are getting this as dk is equal to c square dm. For total increase in kinetic energy, taking integration, we can get the value as k plus m0 c square, which is equal to mc square. So by adjusting the terms, we can get final answer as E is equal to mc square, which is nothing but E is nothing but total energy, potential energy plus kinetic energy. So we are getting this value as E is equal to mc square, which is called as Einstein's energy mass equivalence relation. So let us move to the next point, that is mass defect. So mass defect is nothing but it is the difference between the rest mass of the nucleus and the sum of the masses of the nucleus composing a nucleus is known as mass defect. So how we can determine this? It is the difference between the rest mass of the nucleus and the sum of the masses of nucleons. Nucleons means protons and neutrons. So by considering this, we can get the delta M. Next is binding energy. It is the energy required to break up a nucleus into its constituent parts and place them at an infinite distance from one another. So binding energy is nothing but the energy utilized to bind that nucleons, which is nothing but delta M into C square. Next is nuclear forces. They are the forces between proton-proton, proton-neutron and neutron-neutron in the nucleus. They can be explained by meson theory. So we can get these nuclear forces, which are the forces between nucleons, that is proton-proton, proton-neutron and neutron-neutron. So we have discussed these points. What is meant by mass defect, that is delta M, total mass, and the sum of the masses of nucleons. Binding energy is to bind the nucleons, so that energy is utilized to bind the nucleons, and is nuclear forces between protons and neutrons, so we have discussed. Next is binding energy curve. So if we check this binding energy curve, it is atomic mass number and average binding energy per nucleon in million electron volt. So if we check carefully, as the atomic mass number increases, here initially this binding energy R also, that binding energy is also increases and it reaches to the maximum term, that is 8.8, and after that, that is from 60 to 80 if we consider, after that it is slowly decreases as atomic mass number increases. So it is because the binding energy between nucleons, as we know that atomic mass number increases, here initially the energy is increases with atomic mass number, but as repulsion takes place, so afterwards that binding energy slightly decreases. So let us check the features of binding energy curve. So what are the features? Let us read it first. First point is binding energy per nucleon of very light nucleus such as 1H2 is very small. Initially, there is a rapid rise in the value of binding energy per nucleon. Means in initial stages, there is a rapid increase in the binding energy per nucleon. Between mass numbers 4 and 20, the curve shows cyclic recurrence of peaks corresponding to different elements, that is helium, carbon, etc., oxygen. This shows that the binding energy per nucleon of these nucleides is greater than those of their immediate neighbors. Each of these nuclei can be formed by adding an alpha particle to the preceding nucleus. After value 20, there is a gradual increase in binding energy per nucleon. The maximum value of 8.8 million electron volt is reached at the value capital A is equal to 56. Therefore, iron nucleus is the most stable. Next point, binding energy per nucleon of nucleides having mass numbers ranging from 40 to 120 are close to the maximum value. So these elements are highly stable and non-radioactive. Beyond 120, the value decreases and falls to 7.6 million electron volt for uranium. So as we have discussed that from 120, if we check, this slowly decreases and it reaches up to 7.6 for uranium. Next, beyond the value 128, the value shows a rapid decrease. This makes elements beyond uranium quite unstable and radioactive. The dropping of the curve at high mass number indicates that the nucleons are more tightly bound and they can undergo fission to become stable. The dropping of the curve at low mass numbers indicates that the nucleons can undergo fusion to become stable. So if we check these last 2 points, they are giving ideas how this nuclear fission and nuclear fusion takes place related to that particular material. So now let us check what is meant by radioactivity. So radioactivity is the phenomenon of emitting alpha, beta and gamma radiations spontaneously. So if we check the figure, that is radioactive substance, if we are checking, it is enclosed in the lead box, so it is emitting alpha, beta and gamma rays. So what is meant by radioactive decay? If we check, the disintegration of radioactive material is purely a random process and it is merely a matter of chance. Which nucleus will suffer disintegration or decay first cannot be told. Next, the rate of decay is completely independent of the physical composition and chemical condition of the material. The rate of decay is directly proportional to the quantity of the material actually present at that instant. As the decay goes on, the original material goes on decreasing and the rate of decay consequently goes on decreasing. So it depends upon the material and how that alpha, beta and gamma particles gets emitted. So the decay takes place related to that. So further, if we check the time in half-lives and number of atoms in capital N, so we can get this equation, that is if capital N is the number of radioactive atoms present at any instant, then the rate of decay is dN by dt, which is proportional to capital N, or minus dN by dt, which is equal to lambda to capital N, where lambda is the decay constant or the disintegration constant we can consider. Then rearranging this, we can get dN by capital N is equal to minus lambda into dt, or integration, we are getting this equation. So if we consider, if at time t is equal to 0 we had n0 atoms, then this log of n0, which is equal to 0 plus c. So if we adjust these terms, we can get the last one, that is n is equal to n0 into e raised to minus lambda t. So if we check the figure, then time in half-lives, if we check, so from n0 to n0 by 2, n0 by 4, n0 by 8, etc. if we go, so we can get this slow and steady decrease. So let us discuss further, that is radioactive disintegration constant. So according to the law of radioactive decay that we have checked, it's dN by n, which is equal to minus lambda to dt. So if dt is equal to 1 second, then we are simply writing this equation. So thus this constant may be defined as the relative number of atoms decaying per second. So we can add this value and then we can get the equation as n is equal to n divided by n0, which is equal to 1 upon e. Thus this constant may also be defined as the reciprocal of the time when n divided by n0 falls to 1 divided by e. So we can write this as t is equal to reciprocal, that is 1 divided by lambda, that is the constant. Then half-life period, how we can check this? So half-life period is the time required for the disintegration of half of the amount of radioactive substance originally present. That is, if t is the half-life period, then we can determine this by this equation as we have discussed already these points. So the time t in which material changes from n0 to n is given by this equation, that is t is equal to 3.323 capital T into log to the base 10 in bracket n0 by capital N. Number of atoms left behind after n half-lives is given by n is equal to n0 in bracket 1 half raised to n, or n is equal to n0 1 half raised to t by capital T. So let us check units of radioactivity. Curie, the activity of the radioactive substance, is said to be 1 curie if it undergoes this times disintegration per second. The Rutherford activity of the radioactive substance is said to be 1 Rutherford if it undergoes 10⁶ disintegration per second. Then the Becquerel, the activity of radioactive substance is said to be 1 Becquerel if it undergoes 1 disintegration per second. So these are different units related to radioactivity. So as we have discussed in binding energy curve, number of that atomic number depends upon that nuclear fusion and fusion process happens. So first let us check nuclear fission. So what is meant by nuclear fission? So nuclear fission is defined as a type of nuclear disintegration in which a heavy nuclei splits into two nuclei of comparable size, and not only we are getting this accompanied by the release of a large amount of energy and neutrons. So what is meant by nuclear fission? So nuclear fission is simply the splitting of a heavy nuclei into two light nuclei with comparable size, and we are getting some neutrons and a large amount of energy is released. So how much amount of energy released? If we check the example of uranium, this heavy element, so if we bombard neutron to this uranium 235, then we are getting barium krypton, that is it gets split into two light nuclei, that is barium and krypton. 3 neutrons gets released and energy of 200 million electron volt we are getting. So in this case we are bombarding this uranium by neutron and we are getting two light nuclei, barium and krypton. Not only we are getting barium and krypton, but 3 neutrons, and from the single fission reaction we are getting large amount of energy, which is of the order of or near about 200 million electron volt. So what happens exactly in the fission we have to check. So here this neutron is bombarding on this uranium, we are getting barium, krypton and 3 neutrons. What happens to the next, which is nothing but nuclear chain reaction cycle? So in this nuclear chain reaction, these 3 neutrons once again bombard on the 3 uranium and they split that uranium into barium, krypton and 3 neutrons further. Then this cycle continues, which is a chain reaction. So it splits more number of uranium and we are getting more number of barium, krypton and further large number of neutrons until that element gets disintegrated or that material gets disintegrated. Then in this chain reaction some terms we have to discuss, that is critical size. So here you can easily observe that neutron bombards on uranium, we are getting barium and krypton plus 3 neutrons. Further these neutrons are bombarded on these 3 uranium. Once again we are getting barium, krypton and 3 neutrons. So this cycle continues. That's why it is called as chain reaction. But some factors are affecting this chain reaction. So let us discuss what is meant by this critical size. So for chain reaction to occur, the size of the fissionable material must be above the size called as critical size. A released neutron must travel minimum through 10 cm so that it is properly slowed down to cause further fission. If the size of the material is less than the critical size, then all the neutrons are lost. If the size is equal to the critical size, then the number of neutrons produced is equal to the number of neutrons lost. If the size is greater than the critical size, then the number of neutrons is greater than the number of neutrons which gets absorbed or released by that system. Then we move to the next type, that is nuclear fusion. So we have discussed the nuclear fission, where what happens, the heavy nuclei splits into two light nuclei. Now in case of fusion, nuclear fusion is defined as a type of nuclear reaction in which two light nuclei merge into one another to form a heavy nuclei, which is accompanied by release of large amount of energy. So opposite to nuclear fission, in case of fusion, what happens? Two light stable nuclei combine together to form a heavy nuclei, and of course in this case large amount of energy is released. So if we check two types of cycles, which is called as PP cycle and CNO cycle, that is proton-proton cycle and carbon-nitrogen or carbon-nitrogen oxygen cycle, also it is called. From that we get idea that how there is conversion of hydrogen to helium, and in this case we are getting large amount of energy which gets released. So it happens in the stars, like for example in our sun, at the core of sun, this continuous fusion occurs, that is hydrogen to helium conversion. So for proton-proton cycle, if you consider, so this proton plus proton we are getting deuteron, then this proton plus deuteron we are getting helium, that is helium 3, and these two helium 3 if we fuse together, then we are getting this large amount of energy by releasing two protons once again. So this cycle continues. In case of carbon nitrogen also, we are adding here protons, and every times that cycle continues to get the hydrogen to helium, which is the last point, that is twice He4, and energy gets released in this case. So in case of nuclear fusion also, though that atoms are fusing together, they are releasing the energy. So hydrogen to helium conversion we have discussed by proton-proton and carbon-nitrogen cycle. Then next point, already we have discussed this one in our previous lecture, but de Broglie wavelength we have to discuss as we are discussing about Davis and Germer experiment. So de Broglie wave. So according to de Broglie, a moving material particle can be associated with a wave. That is, simply we can say that the particle is also showing a wave nature, which is called as matter wave. So by using the two equations, that is E is equal to h nu and E is equal to mc square, by comparing this we can get the equation as simply lambda is equal to h by mv, or lambda is equal to h by p, or we can say p is equal to h by lambda. So this equation we can get by comparing these two equations. So lambda is equal to h by mv, where de Broglie wavelength is inversely proportional to the velocity of the particle. If the particle moves faster, then the wavelength will be smaller, and vice versa. If the particle is at rest, then the de Broglie wavelength is infinite. Such a wave cannot be visualized. De Broglie wavelength is inversely proportional to the mass of the particle. The wavelength associated with a heavier particle is smaller than that with a lighter particle. De Broglie wavelength is independent of the charge of the particle. Matter waves like electromagnetic waves can travel in vacuum, and hence they are not mechanical waves. Matter waves are not electromagnetic waves because they are not produced by accelerated charges. So we can say matter waves are probability waves, amplitude of which gives the probability of existence of the particle at the point. So these are the conclusion points for this de Broglie wave or matter wave. Then if we consider the practical proof of this, so this is nothing but Davison and Germer experiment, where a beam of electrons emitted by the electron gun is made to fall on nickel crystal cut along cubical axis at a particular angle. So if we use this electron gun and we are bombarding these scattered beam electrons, which are gets received by detector here, so we can check the angle, and we are exposing that to nickel crystal which is cut along particular angle. So the scattered beam of electron is received by the detector, which can be rotated at any angle. So we have made this detector to rotate so that we can detect the angle. The energy of the incident beam of electron can be varied by changing the applied voltage to the electron gun. Intensity of the scattered beam of electron is found to be maximum when angle of scattering is 50 degree and the accelerating potential is 54 volt. So at different angle and at different accelerating potential, we are detecting these signals, and after that we are plotting the graph. From that we can get the idea that the intensity of scattered beam is maximum at a particular angle, which is 50 degree, and at particular accelerating potential, that is 54 volt. So we know the Bragg's equation, that is 2d sin theta is equal to n lambda. So we are comparing this with the Davis and Germer experiment calculation, and we can prove the things that how these particles are also having wave nature, that is matter waves. So at these different intensities with different accelerating potential, if we check, so at 50 degree angle and at 54 volt, we are getting the maximum intensity, which is shown in this graph clearly. So the de Broglie wavelength of moving electron at V is equal to 54 volt is 1.67, which is close to agreement with 1.65, that is lambda for Bragg's equation. So it is practically proved that how these matter waves are there. So now we have discussed the points related to these atoms, molecules and nuclei. Now let us check few MCQs related to these points. So before starting these MCQs, let us check what we have discussed. We have started with the basic terms. Then we have checked relativity of mass, then radioactivity, what's meant by atomic number, atomic mass number, then E is equal to mc square equation, nuclear fusion, then de Broglie wave, it's a practical proof, that is Davis and Germer experiment. Now let us discuss the first MCQ. So I read it first. If R is the radius of the lowest orbit of Bohr's model of H atom, then the radius of nth orbit is, so here we know the equation, that is Rn is equal to R1 n square. So simply we can get the answer as Rn square. So the answer is Rn square. Next we can use the same equation, that is if the radius of the first Bohr orbit of H atom is 0.5 angstrom, the radius of the third orbit will be, so for third orbit, that is Rn is equal to R1 n square. So R3, that is third orbit, we can write the value as the radius is 0.5 angstrom. So 0.5 into 3 square, we can get 4.5 angstrom, which is the answer. Next, the series limit wavelength of the Lyman series for the hydrogen atom is given by, so for Lyman series, P is equal to 1, N is equal to infinity. If we put the values, we can get answer as lambda is equal to 1 by R. So it is the answer. By putting it, we can get the answer. Next, the series limit wavelength of the Balmer series for the hydrogen atom is, so in this case, P is equal to 2, N is equal to infinity. After putting the value, we can get the answer as 4 by R. Then let us discuss this next MCQ. The mass of an electron at rest is 9.1 into 10 raised to minus 31 kilogram. The mass of an electron when it is moving with speed of 2.4 into 10 raised to 8 meter per second is given, that is the value of C, 3 into 10 raised to 8 meter per second. So two conditions are there. The mass is at rest is given to us, and we have to determine the mass of an electron when it is moving with certain speed. Its value is 2.4 into 10 raised to 8 meter per second. So we know the equation, that is relativity of mass, which is m is equal to m0 divided by under root 1 minus v square by c square, where m0 value is 9.1 into 10 raised to minus 31. So 1 minus value of v, we know 2.4 into 10 raised to 8 meter per second, and value of c we are putting. So after solving this, we can get the answer as 15.17 into 10 raised to minus 31 kilogram, which is our option B. Next, the speed of a particle whose kinetic energy is equal to its rest mass energy is. So for that, we have to first use the equations, and then we can, comparing the equations, we can get the answer. So here numerical value is not given, but the condition is given: the speed of a particle whose kinetic energy is equal to rest mass energy. So rest mass energy is m0 c square and kinetic energy is 1/2 m0 v square. So as E is equal to mc square, so after comparing this, we can simply get m is equal to 2 into rest mass, that is m is equal to 2m0. Now we know the equation, that is m is equal to m0 divided by under root 1 minus v square by c square. So put value of m as twice m0. After putting this, we know the value of c, and we can determine easily the value of v. So as this MCQ is without numericals, but we have to know the relation, and from that we can get the answer. So let us check next point. The wavelength of de Broglie wave is 2 micrometer, then its momentum is, so value of h is also given. So it is very simple, that if we know the equation, p is equal to lambda, p is equal to h by lambda, so we can just adjust the term. It's p is equal to h by lambda. After putting the value, that lambda is nothing but 2 micrometer, 2 into 10 raised to minus 6, we can easily get the answer. So these are some of the MCQs we have discussed, which are related to de Broglie wave, relativity of mass, then Lyman series, Balmer series, etc. So I hope that you got some of the points, some ideas related to these equations, what we have discussed, and some of the MCQs what we have solved. So in first part we have discussed some basic terms. In the second part we have discussed some of the MCQs. So we conclude here. Thank you for listening and watching this video lecture. Thank you very much.